All right, so I'm Azza Abouzied, and I do work at the intersection of data management and HCI. I want to give you a brief intro about myself. Okay, now it works. So, like Michael said, I started out as a database researcher. In fact, my first few projects were all pretty much back-end databases. How can we make it run faster? How can I help the Yahoos and the Googles with their large data? How can I run a query in a sub-millisecond time instead of, 10 milliseconds? And then something happened, right? I got tired of sort of helping the Googles and the Yahoos, and I wanted to help normal folk with their data. And so I flew all the way from the East Coast to the West Coast. It was that transformative in terms of what I needed to do, and started working with Joe Hellerstein at UC Berkeley. And in fact, when I joined, it was a semester. We would look at a few problems, think about what we want to do to help users with their data. Joe suggested that I come attend the data visualization course here in Stanford taught by Jeff here. So I spent a semester, I wasn't even formally auditing, I would just crash his course. It really helped sort of formulate my ideas about what it means when people look at data, how do they see and understand data. And that sort of guided a lot of my research. So since then, I joined the faculty at NYU Abu Dhabi. We actually are located in a place called Saadiyat, which is, whoops. Better? Okay. So Saadiyat literally means happy island, so we've been happy since. And I've been working mostly on what I'd like to call example-driven interfaces. And I'll define that a little bit later in my talk. There has still been some back-end database research that I've been doing, and I like to sort of keep my foot in both places. And there's a whole slew of projects that I've built that are sort of, that fall under this umbrella team of example-driven interfaces. So that's it about me in terms of, my professional research life. On my personal life, I just had a baby who's 9 months old, and he's been tagging along with me. If you see a screaming, crying baby and a lost dad, that could be my husband and son roaming around in Stanford. All right. So I guess that's it for an intro. I'd like to start the talk by sort of engaging in this thought experiment with you. I want you to sort of think for a few seconds about how you would describe what furniture is. Perhaps to somebody next to you, perhaps to an alien. What is furniture? Does anybody want to volunteer a definition or just an explanation of what furniture is? Sure.
Maybe objects in your home that have practical use.
Okay, that's a very thought out and abstract definition of what furniture is. If you thought of a couch or a chair, maybe you even thought about a table, then perhaps you're a database person. But that's normally what people would do, is sort of think about a concrete object, right? And when you talked about objects around in your home, you were sort of reflecting on things that define what furniture is. But you referred, or you thought about, or you reflected on an example, right? So if you did that, then this is what cognitive scientists would basically call exemplar-based reasoning, prototyping. You sort of fell back on a prototype. And that could be a chair, a couch. It could differ from person to person, but the idea is that you went back to an example. And this sort of mode of thinking is very pervasive. People have studied firefighters and how they sort of deal with situations. When they look at a fire, they don't necessarily reflect back on the manual. They reflect back on a similar fire that they've seen, and then decide what their next action is. When they've studied radiologists looking at X-rays of tumors, again, they don't necessarily think about, what are the X many characteristics of what a tumor is. They sort of reflect back on similar tumors that they've seen and how close the current X-ray is to those past examples. Now, many other fields have latched on this idea that we think with examples or we communicate with examples. Advertisers or marketers, for example, will sell you examples of how an object is used when trying to promote it, right? If you've looked at the Fitbit website, you've got all these, fit people sort of promoting the Fitbit, right? And it's so pervasive, I went ahead and bought a Fitbit thinking I'd look like those people, and that never happened. And I don't really use the Fitbit that much, but I do own it, right? People use that when seeking advice, right? People go buy Trump's, how do you negotiate, the art of the deal, right? Or in this case, they buy, Tom Brady's book to sort of figure out what they want to do to sort of get into a stronger, fitter shape. There was a phase in my life where I was like, I need to get back in shape. And so lots of money spent, not much in terms of like what happened. All right, so I want to use this idea of examples to help people communicate with their data tools and get the most out of it. Right, and so from that, this whole idea of an example-driven interface came to mind. And I want to be a bit more specific about it, a bit more concrete, to use an example of what I mean. Right? So suppose I want to buy a box of chocolates. Right? In the normal form, we'd go to a store, we'd meet a chocolatier, and we'd say, well, I want to buy a box of chocolates. I want it to have some white chocolate, some dark chocolates. And then we'd work together in a series of conversations, right, or questions. He'd say, well, do you want it like this? And I'll be like, no, maybe I want more dark, or maybe I want less nuts, right? And then he'd ask me for a few more options, right? But the thing is, we'd work together through a series of questions and answers where we're mostly sort of asking, does this example fit your needs or not? Right? And finally, we'd end up with the perfect chocolate box. Now, how you'd interact with a database is completely different. Suppose I replace this chocolatier with a database. Then my mode of interaction would basically be issue this horrendous SQL query, which may or may not be correct, right? And I'd have to think about it right at the get-go. I have to formulate a very precise idea of what I want because the language is very precise. And so I'm possibly going to get that first formulation incorrect. And it doesn't matter that, it's not exactly what I want. I'll issue it anyway against the database. I'll potentially wait a long time depending on how difficult the query is or how many chocolates exist in that database. And then I'd end up with lots and lots of boxes that define or that sort of are correct answers for the query. But they may not be correct answers for what I intended. And I'd have to sift through them to pick one or go back and reformulate my query. So the two forms of interaction are very different, and clearly we want something more humane, right? And so what I mean by an example-driven interface is something that sort of mimics that chocolatier in that it allows us to specify what we want, perhaps ambiguously, perhaps vaguely, and then work with us in a series of interactions towards a more precise definition of what we want. Right? And you could use these EDIs for a variety of tasks, and that's what we did in our research, is sort of use these EDIs for data extraction, for debugging data pipelines, for SQL queries. That was my very first project. Even for data generation, I show an example for time series querying later as well. So the rest of the talk is basically outlined like this. We've already sort of given an idea of what these example-driven interfaces are. I'll be talking about why now is the right time to look at these, how to build them, sort of a quick recipe for how you could put together an EDI, and then sort of discuss when things work and when they don't. Right? So I wish I could say every time you design an EDI, it's going to work. We've seen more failures than successes, and I'm going to go through an example of that. And then where do we go from here? What's next? If you want to do this kind of research, what should you do? Or what I think are interesting venues to look into. Okay, so why now is the right time? And it's a fair question because this idea of doing things by example existed for a while, right? This is a very early paper in my community, in the database community, on query by example from the 1970s. And it never took off, right? It's a very well-cited paper, but there hasn't been any sort of known or widely used example-driven, or at least the way Sleuth intended it, interfaces for databases. Well, the reason I think now is the right time is because since then, there are a variety of fields that have matured in computer science. And if we look at the confluence of them, we have so much power now that we could make them work. We could make these interfaces do things that we couldn't have made them do previously. And the very first research area that matured is this program synthesis area. So it started out very early by Church, where he looked at sort of simple circuit synthesis, right? It was that's kind of boring. That's not what you want to do with your data right now. But since then, there has been lots of work in terms of, well, how can you use more than just examples? Suppose I give you examples of what the input and the output should be, but I also give you a simple program sketch. And so then the work of Solar Lezema came in, and it sort of looked at ways to make this efficient, right? There's a huge space of what programs are correct given a few input-output examples. Searching that space needs to be efficient if you want this to sort of occur within an interaction time, right? You do not expect your chocolatier, you give them an example of what you want. You say, I want a box with some white chocolates, and then disappear for 10 minutes and come back and be like, is this close to what you want or that? You want sort of quick interaction times, right? So efficiency is key when you're trying to synthesize these programs, these queries, these data extraction scripts, and so on. And since then, PBE, or programming by example, has become mainstream. Do any of you use Excel? Everybody does, right? Has anybody tried out the flash fill feature? 2. The researchers in the room. Have you used it for actual tasks? Okay, cool. We've got one person who did. It's pretty cool. Try it out. You basically give a few examples of what you want, let's say, differently formatted telephone numbers, and then, how you want the telephone numbers to be formatted. And then you say flash fill, and it will automatically transform all your telephone numbers. So you could do that with any kind of data, formatting first names, last names, what you want, addresses. So it's pretty cool, and now it's mainstream. The second area that has sort of evolved, and this comes from HCI, is this idea of mixed initiative user interfaces. How many of you know who Clippy is? Right? It's the most annoying thing, right? Or not. There's a huge debate now. But for people who used Clippy, which I remember was during my high school years or something, I found it really annoying. I found that Clippy interferes way too much, gives the wrong advice all the time. The idea was pretty cool, but it was automation done in an invasive form. And if you think about these EDIs, they're in a way trying to automate the construction of a query, the construction of a data extraction script from a few examples. So there's automation involved from a few human interactions. And so you have to be careful about how you design it. And Clippy, I would say, was a great idea done wrong, right? So since then, Eric Horvitz's work came out, which sort of outlined principles of how you should design these mixed initiative user interfaces, where the user does a little bit, and then the system sort of tries and automates from there. Now, since then, Clippy died, which was good news for all. I think by Clippy, going to his grave, it sort of allowed room for all these interfaces, or for the idea of automation to come back again. In the correct way. And so we have tools right now, for example, for data wrangling or data cleaning, like Trifacta, where it would suggest at every interaction, you click a column, it will suggest ideas for how you want to transform that column. You highlight something, it will suggest scripts for what you want to extract based on what you highlighted. And it's sort of this predictive interaction at every step that the user takes. So I think that those ideas are sort of really helpful when it comes to designing these example-driven interfaces. The third area, and there are 5, so we're getting there, is learning theory or active learning. And the reason why this is important to us is active learning helps us sort of expand the examples that we have to learn the correct behavior from, right? If you provide only a few examples and you try to infer what the program is, you could be very much underspecified. And what active learning allows us to do is not only ask the right questions to sort of get more informative examples from the users, but it also allows us to sort of learn scripts to learn what the user thinks is a correct or an incorrect example to then feed into the program inference stage. So active learning can really expand the examples that we have, allowing us to generate more correct programs or scripts of what the user wants. And there's really interesting work by Chris Ray, who's at Stanford and does data management research on sort of active learning through this tool that he built that's called Snorkel. So if you're interested, please go and check it out. The other thing that's important is this research in causality and explanations. And really it started as a field in philosophy, right? And then moved on into AI, and now it's becoming even more important in the database area, because if you get a certain output from a data transformation or a data exploration script, you want to know why it came about. And so causality and explanation sort of explain, sort of work backwards through the provenance, through the lineage of the data to explain why something is an answer, right? And there's been a lot of research in this area, and I think it's really important for EDIs because you have that aspect of automation. You might want to know why a certain script was chosen by your EDI as the correct script, or why a certain query was picked by it, especially if it didn't meet your needs. And finally, the last area of improvement that occurred in the span from the 70s up till now is visualization, and automated visualization and declarative languages for visualization. And the more visualization research improves, the better it is for data research in general and data interfaces, because we like to think of our data visually, right? It is impossible to think of a million tuples if we're given a table, right? But it is much easier to make sense of it if we have the correct visualization in place. With that in mind, if I have a beautiful visualization of my data, interacting with it is the next important step, right? And so interactive visualizations, which are going to become easier if you have clean languages for visualizations, help us sort of extract examples from the users of what they want, which in turn helps us to appropriately query, analyze the data, and so on. All right. So now that these areas have sort of given us what we need to sort of build these EDIs, how can we actually go about and build them, right? And this is sort of a very quick and dirty recipe that you could get from reading Sumit Golwani's book on program synthesis. And he sort of defines a few dimensions. And really, he says 3 dimensions: intent specification, search space, and search techniques. And I add an ambiguity resolution as a 4th important dimension there. So what does that mean? Well, the first thing is you want to figure out what's the most natural way to get what the user intends to do with their data. Now, in some cases, it could be, here's my data, here's what I want the output to look like. In some cases, that's very difficult to get from the user, or it's very unnatural to ask the user to do that, right? Or it might just be too underspecified at that case, and you need a little bit more. Perhaps you need hints of what the query should look like, or you need hints of what the analysis should include. Sometimes you just need to provide binary, answer, not answer. So these are what we could call positive or negative examples. And in some cases, like I'm going to show later, perhaps a sketch, a drawing of what they want, right? The search space is the next very important task. And remember that when you're thinking about data analysis scripts, the space is enormous. Even simple queries, even simple Boolean queries, sort of queries that return answers or non-answers as their result, that space is massive, right? It's astronomical. Searching it, given one or two examples, is a problem. So what you end up have to doing, and really this is where a lot of the art in building these EDIs comes in, is sort of trying to decide how can I scope it out in a way that makes sense. And sometimes that scoping it out comes from observing your users, seeing what are the most commonly, what are the most common tasks that they do, and perhaps that defines your search space, right? Perhaps it comes down to defining a language that's simpler than what you can do with your data, but sort of expressive enough and powerful enough that the users like it, even though it's a simplified version. But it gives you the added benefit that the space of programs you could construct with that language is small enough that these things become tractable. And so, this art is also known as sort of creating a syntactic bias, right? You're creating a language with a certain syntax that biases the programs that you could generate in a certain way. And there's a lot of research in terms of how do you get program synthesis right? How do you define or scope out your search space? Some people will say it's advantageous to create operators in your data transformation or analysis scripts that are invertible, right? You give it an input, it gives you an output, you pass back the output, you get back the input. And this is also very important if you're doing sort of step-by-step synthesis, where you're sort of suggesting an operator at a time rather than a whole program or query or script at a time. Then the search techniques sort of, that's the third dimension you need to think about, is how do you sort of figure out what the most appropriate program or script is, given the language, given the scope that you've defined. And again, there are plenty of techniques, and by looking at sort of the latest and greatest in program synthesis, you could sort of pick and choose what you want to use. You could use an SMT solver to help you, or you could use brute force search, right? Or you could even sort of create these nice version space algebras, which basically say, I'm going to store the minimum and the maximum of the programs that you have, rather than everything that's possible given your examples. And then ambiguity resolution is the fourth dimension, because you need to come back to the user, right? You need to come back and say, I don't have enough data, I don't have enough examples, give me more. Or I think it could be one of these many programs, which one is it? And how you do ambiguity resolution is, again, part of the HCI fun that gets into this domain. Okay, so any questions so far? We're good? All right, so when do these work? And we could take a very narrow definition here of working, right? For me, these EDIs work if you could complete a data task in much shorter time, more accurately than the sort of run-of-the-mill tools that you have that require you to specify things in a language or a script or a query, a language like SQL. Right? So that may not be the best definition of success, but it's something that we could measure and evaluate. All right, so the first tool that I built is DataPlay. The idea there is that you have these queries that are basically Boolean queries. So they either give you answers or they split your entire data set into answers or non-answers. So the example here is something like, oh, I want to find out all students who are straight A students, for example. And so I could sort of either, and the way this starts is I need to give a few hints of what my query ought to be. So the hint here is something like, grade equals A. So you could give these small predicates. You don't give the full query, but you're giving small predicates that then the system sort of assembles in a complete query for you. After you go in here and you say things like, I want to keep the student in because they're a straight A, but I want to keep the student out because, maybe they're not straight A students, right? By basically sort of just interacting with the want out, keep in, want in, keep out, you could sort of structure the query correctly to meet your needs. Now, one of the things we've learned by building DataPlay is that, examples alone generally are not enough. You need a little bit of hinting from the users. And in our case, and you want to keep the hints simple. So we said, well, any user can write simple predicates. You could write things like they should be in the CS57 course, right? But it's much difficult to say something like they should be taking all courses that are offered by the HCI school, for example, right? So simple predicates are easy, but once you sort of quantify them, it gets more and more complicated. So maybe that's where you need these examples to help you sort of structure the full query, right? Or you could think about your predicates easily, but putting them in a conjunctive form or a disjunctive form, that might be tricky. So perhaps we could help you with that. The second sort of tool that we built was around example-driven data extraction. So the idea here is you have this journalist looking at FBI data press releases, and they're trying to figure out, has crime increased or decreased over the past few decades or something. Or wait, this is a different one. But yeah, that was one of the tasks we did. Here it's a simpler example. We're just extracting dates from the data set. And so I could highlight what I want, and then it would suggest sort of different extraction rules. And I could sort of go in and say, I could highlight something and say it's not an example of what I want. And then, from the rules, I could look at them. But also what the system does for us is something smart, where it sort of looks at what can be extracted by all the possible rules that are currently valid, and then allows you to sort of say, keep in or not, right? Perhaps you want full dates, but not May 2011. So you could go and sort of say yes, no, depending on what is currently the valid space of rules, given what you just highlighted, right? So it allows you to sort of, it helps you guide, or it helps you sort of guide the synthesis by asking you sort of mark these tuples or mark these extractions. They're more important than just going through the document and adding more extractions to it. Okay, so again, this idea of going back to the user and asking them to sort of help you distinguish between what you want or don't want helps a lot with these EDIs. Qetch is another interesting tool that we built for time series querying. So time series are things like stock prices, heart rate, anything that changes over time is a time series. And what we found interesting here is that the most natural way of providing an example of what you want is just a sketch of the pattern, right? It's not this time series in and this time series out. It's this is what I'm looking for, and it's just a sketch, right? And then what was really cool about us building Qetch is that when we built it, we sort of went top down, right? We looked at what the interface ought to be, and that in turn changed how we designed our time series matching algorithms. And we found that the sort of state of the art that's used by database systems, like dynamic time warping or even Euclidean distance matching, just weren't good enough for matching sketches to time series data. So we had to recreate a good matching algorithm for the task. And this is what I like about sort of doing this intersection research, is that you end up sort of doing things that impact multiple fields at a time. Right. And there were several neat things that we did with Sketch. This idea of you have a canvas, you draw on it. Well, what more can you do with the drawing, right? So we came up with sort of a new sketch-based language where we said, well, maybe I could do regular expressions over here. Can I mark part of my sketch and I say, I want this part to repeat, or I want this but not I draw something and I say everything but what I just drew, for example. So a whole regular expression on top of sketches. And then we also did a few cool things like, where I draw something on the canvas sort of helps me decide the order of things that I want it to appear in a time series. So sort of relative positioning of your sketches creates an ordered query for you. Synner is an interesting tool that we're currently building. The idea there is you generate data that you want by example. So you go in and you fill a few things, and then it figures out from those examples what the domain of the data is, what relationships exist to that domain, and perhaps suggests those to sort of introduce into your data. It can figure out things like what the statistical distribution is from the few examples that you gave and suggest that. Perhaps you want to generate numbers from a normal. Will help you then later go back in and tweak it. And then what we also realize is that when you generate data from a statistical distribution, people have trouble sometimes understanding that if you want a normal curve, when you actually generate the data, it's not going to fit that normal curve exactly. So we had to do some cool visualization tricks to show them, that yes, you've specified the Bell normal curve, but all of these sort of little things are possible, data sets that we could create, sort of giving them this idea that there's a bit of uncertainty here when you generate data statistically. So again, what that sort of tells us is when you build these tools, you have to sort of look at things and say, well, maybe I need to tweak how I visualize the data back to them to give them the sense of what is possible or not possible from the tool. All right, so I gave you 3 successes. What about the failures? I'm only going to show you one, but there are more, and we could talk about them later. This was a joint project with IBM where they have these data pipelines, and then the end users look at the outputs. And they could be wrong, but they can't really figure out where in the pipeline the error was introduced, where the bug was. But because they could look at the outputs and say this is correct or incorrect, these are examples that perhaps we could use to debug the data pipeline. So we created this system called WhyFlow. And the idea is that they'd look at these outputs, they'd say what is correct or incorrect, and then we'd sort of backpropagate through the whole pipeline, where this correct versus incorrect flow to sort of figure out which module could be the source of the error. But in addition to sort of localizing where the module is, we also wanted to generate an explanation that says, we think the error is at this module, and this is the explanation of what that error could be. Now, it worked and it didn't work in a way. In a way, it did help the sort of the end users localize the error, but they did that much longer than if they manually went through and sort of debugged it. So that's the failure, but they did it more correctly when they used our tool than when they did it manually. Right? So manually, they were more confident of where the error was. They returned back at a much quicker time and said, we think this module is the cause of the error, but they were wrong more often than with our tool. So why did it not work? Well, we think there are several reasons for that. And one of them is this, yes?
Sorry, why does it not work if it's slower? I could very quickly write a program that fails, but it takes me a long time to write a program that works. So why is it bad to get the right answer more slowly?
Because the whole point was to sort of allow very quick round trip times, right? We wanted these end users to sort of figure out these errors and push them back to like the correct team in these data pipeline teams to sort of, reduce the round trip time to an error. And so if I push, the idea is that if I push it to a development team, they have their time to sort of come back and fix it. And if I push back something that's incorrect, they're going to spend their time and they're still going to debug it. But then I did not reduce that time back. So I think it was a business requirement that they wanted these end users to sort of figure out the error quickly and push it back to the correct team. That said, I think there's also, there's the numbers sort of say that, but it was more, like we were 70% better versus 60% better. Like, yes, they were more correct using us, but not by enough of a margin for us to feel happy with what we produced. So that's, I think, one part of it. Yeah. So I guess not enough for us to go like all guns blazing and be like, we created the best debugging tool in the world. Like we just felt very lukewarm about our results. And part of the reason we think we didn't do so great was this idea that you could debug by just a few examples of what is correct and incorrect. Debugging is a super hard problem, right? You're not only generating a space of possible problems, you're sort of doing a second order kind of thing, right? All the programs that ought to be fixes for the current program that's incorrect. And so we did not get the balance right. We needed something more than just labeling. The other thing was that our setup was that we only use what we call Y provenance. This is sort of a database idea where basically you're only tracking what makes it to the output, right? And what we needed was why not provenance, which includes things that did not make it to the output, so sort of dropped results, missed tuples, and so on. And because we didn't have that aspect, there were many errors that we couldn't actually capture. The other problem was that our search space, our explanations that we created were too simplistic. So our idea is that these end users, they're more comfortable with sort of the problem domain, but they're not as comfortable with the modules. And in fact, the modules were black boxes to them. So generating an explanation for what the error could be at a module, we wanted to keep that language as simple as possible. So it was simple predicates. The problem is you simplify the language too much. Now you can't actually capture the error with it, right? Or the script, the explanations that you generated were kind of loose, right? They had low precision. All right. The other problem was that we tried to use probabilistic error models to sort of better localize where the faulty module could be, and sort of also create that syntactic bias. But the problem is these models only worked if you kind of knew how modules could, what were the more likely errors in a module than another, right? So for example, if I have a filtering module, then, a common error is that I got my threshold wrong. Or I said, greater than when it should have been less than, right? And I have a probabilistic model that describes how likely one error is over the other. Now, if I do that, I could get better localization of where the fault can be and perhaps better explanations that sort of fit how programmers commonly create errors. But then I break this black box assumption that we were working with. And then ambiguity resolution was the last problem. And this is really the key HCI problem that we saw there, was that we gave these explanations and we ranked them by measures like precision and recall. And you'd end up getting a lot of explanations with the same precision and the same recall. So we basically are just doing a dump of explanations and asking users to sort of figure out what could have been the cause of the error. And so this sort of ranking was just not right. It wasn't sufficient. We needed something a bit more powerful, but we couldn't figure out what it is. So what did work was the visualization aspect, right? People liked us differentiating correct and incorrect flows. And that helped them trace the source of the error better than any probabilistic sort of error modeling scheme that we used. So in a way, by just visualizing error flows, they themselves manually could sort of interact with the tool and figure out the error better than if that wasn't available as a feature. So in hindsight, everything looks great, right? Okay, so where do we go from here? And these are my last two slides. I think there's a lot of research that could be done on the HCI side, especially around how we visualize these synthesized artifacts. How do we visualize the space of programs, given a few examples? And the idea is that if I could show you that, then a user, and if I show you that in a sort of, in a way that's not too intimidating, right? Like, we still don't want to like dump at them a whole bunch of, say, Python scripts, right? I want to show them a space of possible programs in a way that they could interact with that space and say, oh, I think it's more this program than that. So how can we do that in a way that's intuitive to the users? And also do it in conjunction with the examples that they've already given us and the data and its effects on the data. Right? So this is sort of a co-visualization problem that's very hard. And if we could sort of think about how do we visualize programs with respect to their effect on the data, that would be very important. And I don't think there's a lot of research in that space. But there are some things that are coming out, and this is becoming more and more important because people now are dealing with machine learning and multiple models that sort of exist and trying to figure out what is the best model given their data. Right? And then there's a lot in data research, sort of my home field, in the sense that when you build these interfaces, they sort of really change how you do querying and how you do you know, I've given this example of Qetch and how it changed how we did time series matching. But if you think about it at a bigger scale, the pace at which interactions happen when you have these example-driven interfaces is so fast, right? You have a series of incrementally different queries coming out from the user, and you want to be able to support them at sort of millisecond speeds. So that sort of changes the dynamic that we have with the data. We're no longer issuing a query that's the correct query and then waiting for our results. We're issuing a series of queries, potentially. And we're also differentiating between these queries to sort of figure out a way to help the user guide us to the right query. So there's a lot of exciting opportunities in the data itself, in data research and data management itself, to support these interfaces. So that's it for all, and I'm happy to receive your comments and questions. I hope I'm within the time limit.
All right, well, let's thank our speaker one more time.